In our previous lecture, we studied how to construct connected spaces from the given connected spaces. But the question is, where can we find those connected spaces to construct the new one? And to answer this question, the best place to start with is the real line. Since in our previous lecture we have seen the real line or the set of real number is a connected space. So in this lecture we're going to study connected subset or subspaces of real line, and also we will discuss a special type of topological space which is called path connected space. Okay, in order to describe subset or subspace, connected subset or connected subspace of the real line, I'm going to give a theorem without proof. In this theorem, it describes all the connected subset or subspaces of the real line. So here is the statement of our theorem. And this theorem will describe all the connected subspaces or subset of the real line. And the statement of this theorem is a subset E of the real line, a subset E of the real line are containing at least 2 points. A subset E of R containing at least 2 points is connected. It's connected if and only if E is an interval. Okay, so you can see this theorem has if and only if condition. If and only if condition, that means two-side implication. So this theorem, it tells us that if E is a subset of R containing at least 2 elements, then E is connected if E is an interval. And also other side, if E is an interval, or if E is a connected interval, then E has to have at least 2 points, and which is going to be connected. All right, so this theorem, it tells us that any intervals in R is connected. Just let me, no matter the interval is finite interval, infinite interval, open interval, closed interval, half open interval, if you have any interval in R, it's connected. Just let me write as a note the list of intervals in R, and obviously those intervals are going to be connected because of this theorem. The intervals in the real line, the intervals in the real line are those. Okay, just let me first list finite interval. This is open interval. This is half open interval, left side open, right side close, half open interval, left side close, right side open, and this is a closed interval. So these are the finite intervals, and which are simply called the intervals. So based on this theorem, all those intervals are all those intervals are connected, and also infinite intervals. That means negative infinity to a, and thus negative infinity to a, with a is included, and positive a to positive infinity. Sorry, not a could be positive or negative number. uh, a to infinity, and also infinity to infinity. These are the infinite intervals. Infinite intervals, and all these intervals are connected. Infinite intervals, all these intervals are connected in R, or in the set of real number. And in our previous lecture, we have seen R itself is connected, and also is also listed here. Is negative infinity to positive infinity is R. Okay. The next thing we're going to talk about a special type of topological space, which is called path connected space. Path connected space. Okay, so to study path connected space, we are going to use a path. So let's define what is path in a topological space. Okay, so let me first define path and path in a topological space, and then I will give you example, and also will explain this definition. So first let me write it down. Let's say X is a topological space. X is a topological space, and let X and Y, these are any two elements in this topological space. Then a path in X, then the path in this topological space X from this element X to Y is a continuous map F from this interval 0 to 1, both side included, both endpoint included, is a continuous map from 0, 1 to X, such that the image of 0 under F is X, and image of 1 under F is Y. If there is a continuous function F from this interval 0, 1 to X, which satisfy these properties, these two conditions, f of 0 is X and f of 1 is Y. That means image of 0 under F is X and image of 1 under F is Y. Then this continuous map is called a path in X from the element X to the element Y. Okay, so let me just describe this definition of path using a graph or picture, or let's visualize that definition of path here. Okay, so what we have is we have a topological space X. So this is our topological space X. let's say this is our topological space X, and we have 2 points in this space X, which are X and Y. So these are two arbitrary elements in this topological space X. Then the definition it says a path from X to Y is a continuous map from this interval 0 to 1, is a continuous map from this interval 0, 1 to X, such that this guy, the image of 0 under F is gonna be X, and the image of 1 under F is going to be Y. And this map, this function, continuous function, it maps the remaining point or remaining number between 0 and 1 somewhere between X and Y. And so let's say like this, and this is called the this one is called the path from X to Y. So we have a continuous function f from 0, 1 to x, such that the image of 0 under f is x, and the image of 1 under f is y. And this map, this function f, continuous function f, maps the remaining point between x and y. And once we join those images, then you're going to get a path or curve that is called the path from x to y. Okay, so that's a path between 2 points in a topological space. Now, as I said before, we're going to use path to define path connected space. And this space, this topological space X, is called path connected space if for every pair of point in X, no matter which 2 points you pick in X, there should be a path between those 2 points. If there is a path for every pair of point in X, then, or if there exists a path between every pair of point in X, then the topological space X is called path connected space. Okay, let me just write down that definition here. A space X, or is a topological space X, is said to be path connected. It's said to be path connected. It's said to be path connected if there exists a path between every pair of points in X. If for every pair of points there exists a path in the topological space, then that topological space is called path connected space. Okay, now here I gave you the definition of path connected space and also the path in a topological space. Now I'm going to give you a couple of properties, two properties of path connected space. Okay, and the first one is, let me just write down. So I'm gonna give you two properties of path connected space. The first one is a path connected space is connected. In our previous lecture, we have studied connected space, and we just defined path connected space. So one of the property of path connected space is all the path connected spaces, they are connected. Let's prove this statement. The proof of this statement is simple. So let's say X is path connected space. Then we want to prove, or we have to we have to show that X is connected. So we are going to use contradiction method to prove this statement or this property of path connected space. Contradiction method means we're going to assume that this X is not path connected. Okay, suppose X is not connected, because we want to prove X is connected. So as I said before, we are using contradiction method. That's why we are assuming X is not connected. If X is not connected, that means X has a separation. Okay, X has a separation. A space X is called it's called not connected if there exists a separation. Okay, and suppose that separation of X is U union B is a separation of X. That means X can be written as the union of U and B, where U and B are non-empty disjoint open set. These are the non-empty disjoint open set. Okay, so we have like this. This is our topological space X, and we are assuming this is the separation of X. This is our U and B. U and B both are open, non-empty and disjoint. And also, if you look at the assumption, we are assuming X is path connected. If X is path connected, then we can join any 2 points in X by a path. That means for every pair of points in X, there exists a path. So path means is nothing. It is just the continuous function from 0, 1 to this function. This topological space X. So let's say since X is path connected, so as I said before, for every pair of point in X, we can find the path, or we can find a continuous function from 0, 1 to X. And let's say let me assume that that path is this continuous function f from 0, 1 to X. Let this be a path in X. Now here you can see that 0, 1, this interval, this is connected space because it's an interval of R, so it's connected. Since F is a path, so F is continuous. And in our previous lecture, we have studied that the continuous image of a connected space is connected. So the image of this interval 0, 1 under F is connected as being a continuous image of connected space. Okay, just let me write down that thing. So since continuous image of a connected space is connected, this F01, this guy, which is obviously subset of X, is connected. Now here we have a separation of X, and this F of 0, 1 is a connected subspace of X, and we have discussed one of the lemma in our previous lecture, that if there is a separation of X like U and V, and if Y is a connected subspace of X, then that Y, it has to lies entirely either in U or V. So we have discussed that lemma in previous lecture, and if we use that lemma here, since this guy is connected, so U and V is that forms a separation of X. So this guy, the image of this interval 0 1 under F, it has to lies entirely either in U or in V. Okay, it's connected and lies entirely. It lies entirely in either U or V. It cannot be a part of U or part of V. Okay, let's assume that this guy is in U. Then if this image is or image of 0 1 under F is in here, then that means we can find only the path for the points in the U. But if there is a point, since U and B both are non-empty, so you can have a point in U and also you can have a point in B. So we cannot find the path from the point of U to point of B, because this guy, it has to lies entirely in U or entirely in B. So that means we can find only the path either in U or in B, but we cannot find the path from the point U to B, and which is contradiction to X is path connected. If X is path connected, no matter which pair of point you take in X, you should be able to find the path. Okay. Therefore, just let me write down that things here. Therefore, there is no path. There is no path joining a point of U to a point of B, and which is a contradiction. Which is a contradiction to X is path connected space. Since X is a path connected space, so no matter which pair of point we pick here, there should be a path. So, and this contradiction implies that our assumption here, X is not connected, this is wrong. That's why X is connected. So here we just prove that if you have a path connected space, it's always connected. Is the converse of this statement true? That means if you have a connected space, is it path connected? Answer is no. I will give you counter example, okay, in a few minutes. All right, so now let me give you one more property of path connected space. In our previous lecture, we have seen that continuous image of connected space is connected, and that property is also true for path connected space. Continuous image of path connected space is path connected. Okay, continuous image of a path connected space is path connected. Continuous image of path connected space is path connected. The proof is easy, so I'm not giving proof here, but the proof of this property is it should not be hard. Okay, now next I'm gonna give you some example of path in a topological space and also some example of path connected space, and then I'll give you one example of connected space which is not the path connected space. That's the counter example for the converse part of the first property that we mentioned here. Okay, let's start with the some example of path. So I'm gonna give you like here bunch of example. Throughout those example, I is this interval 0 1. The uppercase I is this interval because path is a continuous function from this interval to a topological space. That's why I'm using this I for this interval, and X is a topological space. Now, first two example, they are the example of path in a topological space, and then the remaining examples are like the example of path connected space, and the last one is connected but not the path connected. Okay, all right. So suppose P is an element in this topological space X. Then the constant function f from I to x. Constant function means this function f maps every point of I to a point in x, and we are assuming that point is P. Then the constant function f from I to x defined by f of t, where t is an element of I. F of t is P, where t is an element of I, is a path in x. So it's a path from P to itself, and so if it is path, then it has to be continuous function, and we have seen that in one of our previous lecture. We have seen that constant functions are always continuous. So here we are taking a constant function from I to x defined by this relation. So f is a continuous function, is being a constant function, and for the path your function has to be continuous, so it's continuous. Also it has to map 0 to one end of the path. So we are saying the path is from point P to itself. Since f maps every point of this interval to P, so that means f maps 0 to P and also 1 to P. So it also satisfies the second condition for path. So constant function is a path in a topological space from a point to itself. So maybe you can say is a point path. Okay, so this is one example of path. Now let me give you one more example of path here. Let's say I have a topological space X here, and let's say there is a path between A and B. We have this path from A and B. That means there is a continuous function from I to x such that f of 0 is A and f of 1 is B. So we have a path in this topological space X from A to B. If there is a path, then always we can find a path from B to A as well. So if there is a path from A to B in a topological space, also we can find the path, or there is always a path. There is a path from B to A. So this is another example, kind of obvious example of path. Okay, let me just write down this thing here. Let f from I to x be a path from A to B. So if I is a path from A to B, then it is a continuous function such that f of 0 is A and f of 1 is B. Then the function g from I to x are defined by g of t equal to f of 1 minus t for t is in I is a path from B to A. So if g is a path, then it has to satisfy two conditions. First one, it has to be continuous. Now since g is defined by f, and we know that f is a path, so it's a continuous, so g is also continuous. And then if it is path from B to A, then g of 0, it has to be B. So if you plug in 0 for t here, it's going to be g0, and it's f of 1 minus 0, which is f of 1. But we know f is a path from A to B, so f of 1 is B. That's why g of 0 is B. And similarly, you can find g of 1, which is f of 1 minus 1, which is f of 0 is A. So this is a path from B to A. So if there is a topological space with the path from point A to B, then there is always a path from B to A as well. Okay, the next I'm gonna give you a few example of path connected space. So if you go back to definition of path connected space or topological space is called path connected space if there is a path for every pair of points in that topological space. R, this is R, you have seen this R everywhere throughout our lecture. So R is the real line. This real line is path connected. That means for every pair of point in R, we can find a path. So to show R is path connected, it is easy. Let's say this is our real line that's from negative infinity to positive infinity. If it is path connected, for every pair of point in R, there should be a path. So let's say A and B, these are two arbitrary real numbers in R. Now we're going to show there is a path from A to B, and since A and B are the arbitrary point we are taking, if there is a path from A to B, that means for every pair of point in R there is a path. So finally we can conclude that R is path connected. Okay, so as I said before, to show R is path connected, so just suppose A and B, these are the real number. Now we are trying to find a path from A to B, and you can see in the figure this straight line is going to be a path. But if you want to write down that mathematically, so we need to find a continuous function from 0, 1 to R, so that f of 0 is going to be A and f of 1 is B. So to find that function, let's define a map or define a function f from I to R by this relation. Let's say f of t is 1 minus ta plus tb for t is in I. So we just defined a map from I to R with this relation. Now you can see in this relation, the right side, A and B, these are like the fixed real number, and T is a variable. So right side is kind of polynomial, okay? It's a linear polynomial. And if you have a polynomial, they are always continuous. So f is continuous. So that's the first condition for f to be path. So this if we define the map or function f using this relation, that is going to be continuous, and also it has to satisfy the second condition. Then we can say that then f is continuous because it is a polynomial. It's continuous, and also continuity is not enough. F of 0, it has to be a. So you plug in 0 for t here, that's gonna be a, and you plug in 0 for t here, that is 0. So we got f of 0 equal to a, and then also f of 1, it has to be b. So if you plug in 1 for t here, the first part is 1 minus 1 is 0, and the second part is simply b. So our function also satisfies the second condition. So thus f is a path. So f is a path from a to b. Since a and b are arbitrary real number, that means if we pick any pair of real number, you can find a path. So hence we can say that R is path connected. Okay, and geometrically you can see that R is path connected. So if you pick any 2 points on real line, you can join those 2 points those two real number by a straight line. Next example, let's say we have R2, that is the Cartesian product of R with itself, R2, or let's say the x-axis is R and y-axis is R. And if we consider a unit ball here in R2, unit ball means this is let's say this is the unit circle. I'm sure you all are very familiar with unit circle. So unit ball is the set of all the points on unit circle and also the inner part of the unit circle. So this is called the unit ball, which is called the unit ball in R2, which is denoted by B is 2. So this is the notation that we use to denote the unit ball. So it's basically unit ball is the set of all point on unit circle and also the inner part of the unit circle. So this is called the unit ball, and this unit ball is path connected in R2. Okay, the unit ball B2, which is the set of all order pair in R2 such that x square plus y square it has to be less than or equal to 1. So if x square plus y square equal to 1, you get the point on the circle, unit circle, and if it is less than 1, you get all the point inside the circle. And now obviously from geometrically you can see that if you pick any 2 points on this unit ball, you can find the path. So it's quite obvious from geometrically. But if you want to prove this ball, or if you want to see this ball is a path connected mathematically, then we need to find a continuous map from I to this ball which satisfy both conditions for the path, continuous, and then also the those images. Okay, the unit ball in R2 is path connected. It's path connected. So as I said before, if you want to see why this ball is path connected mathematically, then we need to define a function or map. Let's call that map is f from I to B2 by this relation, defined by this relation. F of t is let's say is 1 minus t let's take those two arbitrary points on this ball B2. First one is x1, y1, and then second one is x2, y2. Let's is x2, y2. Where x1, y1 and x2, y2, since we are in plane, so each point is order pair. So x1, y1 and x2, y2, these are the two arbitrary points in B2, and T is in I. And if we define a function like this, then you can see on the right side is again polynomial, so it's continuous. Define the function by this relation is continuous. It's continuous, and also if we plug in 0 for t, you're gonna get x1, y1, and 1. If you plug in 1 for t, then you're going to get x2, y2. So that means this f is a path from x1, y1 to x2, y2. This x1, y1 and x2, y2, these are two arbitrary points in this ball. Since there is a path for those two arbitrary points, so that means there is a path for every pair of points in this ball. So the unit ball B2 is a path connected in R2. In fact, if you consider the ball in higher dimensional space, like so we are considering in R2. So if you consider the ball in R3, it's like a sphere, every point on the sphere and also inside the sphere. So it's kind of like a solid sphere. That's gonna be also path connected. So even if you take the ball in higher dimensional space, the ball is going to be path connected space. So this is one of the popular example of path connected space. Okay, and now let me give you one more example. Okay, so example number 5. Let's consider R2, which is our regular plane, and then let's make a hole on this plane. Let's make a hole at origin. Okay, so here we are considering R2 without origin. So basically we are considering R2, and then you remove the origin 0 and 0. So this plane is called punctured plane. Okay, and this punctured plane, so basically we are just removing the origin from R2. If you remove the origin from R2, that is called the punctured plane. And also you can remove the origin from a three-dimensional space, and then so on. So but here we are just considering the punctured plane. That means you remove 0 from R2. The punctured plane which is R2 minus 0, 0, is basically you just remove 0 from R2, origin from R2, is path connected. You can see geometrically it is quite obvious. So let's say I have 2 points here. One is over here and one is over here. So if these are my 2 points, then we can join these 2 points by a straight line. If the straight line does not passes through origin. Okay, so that's gonna be my path. But if you are joining those 2 points by a straight line, if the straight line passes through origin, then we cannot say that straight line is a path here. For example, let's say I have a point here and then I have another point here. So if I choose my path as a straight line that passes through origin, this one, then there is a hole at the origin, so it's not going to be continuous. So that does not work here. So in that case, and if you can join those 2 points using the straight line, and if the straight line doesn't passes through origin, that's fine, that's gonna be path for those points. But if your straight line does passes through origin, then what you need to do is we need to choose another point on puncture plane, and then we're gonna join these 2 points and then the other 2 points by using those broken lines. So these broken lines, these two connected broken line, that's gonna be path between those 2 points. That means either using the straight line or by using the broken line, it is possible to find the path for any 2 points in puncture plane. That's why the puncture plane is path connected. Okay, two more example. The next one is quite famous example of path connected space in topology, and which is a unit circle in plane. So we have already seen that the unit ball is path connected. So that means unit circle and also the inner part. But if you even if you remove the inner part of unit ball, then you just left with this unit circle, which is also a path connected space. So it is like this one is going to be 1 1, this is -1 and -1, and which we denoted by S1. Okay, this is called the unit circle, and that unit circle is also path connected. The unit circle, which we denoted by S1, is the set of all order pair such that x square plus y square equal to 1. This is the point, all those points on the circle. The unit circle S1 is path connected. So here we are using S1, and then the circle is in R2. So the notation seems quite confusing, but if you are taking the if you are considering this thing in this space, then it's gonna be a sphere, okay, and which we denoted by S2. So in R2 by S1, in R3 by S2, and then so on. So this unit circle is path connected, and if you simply look at the graph here, it is quite obvious that we can find the path between any 2 points on this unit circle. So that path is going to be, for example, the path between this point and then that point is going to be this part of our curve. Okay, so if you move along this curve, then you can find the path for any 2 points on the circle. So from graphically it's quite obvious, and if you want to see this thing mathematically, then here we are going to use the second property of path connected space that I listed here. The second property, it was let me go back to a couple of slides before. It says continuous image of path connected space is path connected, and if you want to prove S2, or if you want to see S2 is path connected mathematically, then we're going to use that property, which is the continuous image of path connected space is path connected. And we have seen that R2 minus 0, this puncture R2 plane is path connected. Now here we're going to define a continuous map from this puncture plane to S2, and then since this puncture plane is path connected, and if we have a continuous and surjective map from this puncture plane to S2, then using that property we can say that S2 is path connected. So instead of defining continuous map that satisfy those two images property, so we're going to use continuous image of path connected space is path connected, that property here. Okay, so let's define here, let's define define a map f from R2, from this puncture plane to unit circle in R2 or in plane by this relation f of xy. Since we are, the domain of our function is the puncture plane, so that means each point in this puncture plane, they are order pair. So we are defining this map f of x y equal to, what you're going to do is we're going to divide this point by this quantity x square plus y square. It is kind of like a rationalization of a number. Okay, so if you want to rationalize a number, you divide by its absolute value. Okay, for example, if you have a vector and if you want to find the unit vector, or if you want to rationalize it, you divide by its magnitude. So that's what we are doing, something like that here. We are dividing this point by x square plus y square. You can say that is the it's kind of rationalization of this point. So if we define this map like this one, then you can see that this guy is going to be on the unit circle. So if you find the distance of that point from 0, 0, it's going to be 1. Okay, that's why this point is on the unit circle, or in S1. Defined by this map is we have defined a map from puncture plane to S1 using this relation. Then we can say that then f is continuous. Is obviously that one is continuous. You can see that each component, these are like, this is just x square plus y square is like a number. Okay, so x and y, these are like the linear components, so they are obviously continuous. So the whole map is continuous, and also it's surjective. It is easy to see that this one is surjective. So now here we have defined a map, continuous map from puncture plane to S1, and not only the continuous, is surjective. Surjective means S1 is gonna be f of this guy. So surjective means S1 is same as the f R2 minus 0, 0. Okay, so and we know that this guy is path connected and f is continuous. So the continuous image of path connected space is path connected. So this guy is path connected. Since our map is surjective, so this guy is same as S1. That's why S1 is also path connected. So you can write down like this: being a continuous image of the path connected, being a continuous image of a path connected space. Our path connected space is that punctured plane. S prime or S1 is path connected. So here we just prove that the unit circle in R2 is path connected. And even if you go to the higher dimension, like in R3, then the unit circle in R3, that's going to be our sphere with radius 1, that is going to be path connected. So you can generalize this result for in higher dimension as well. Okay, now let me give you one final example. So this is the example of connected space which is not path connected. Okay, so we have seen that path connected space is connected, but I'm going to give you example of connected space which is not the path connected. So the converse of the statement path connected space is connected, the converse of that statement may not be true, which you can see from this example. Okay, example number, so here example number 7. Now let's consider a very famous space in topology which is called the topologist sine curve. Okay, topologist sine curve. This is one of the very popular topological space in topology. It's called the topology sine curve. So let me tell you what is the topology sine curve here. So basically topology's sine curve is the union of those two sets in R2. The first one is set of all xy such that x is 0 and y is from this interval. So basically this is the set of all xy such that x is 0, first coordinate is 0 and the second coordinate is any number between -1 to +1. That is basically y-axis. If you are in xy plane is a y-axis from -1 to +1. So the topology curve is the union of this set with this one, which is the set of all xy, or set of all those points in plane such that x is in this interval, x is from 0 to 1 and y is this sine 1 over x. So the topology sine curve is the union of those two sets. Okay, the first one, like I said earlier, that is that is the part of y-axis from -1 to +1, and the second function is second set is the set of all those points in xy plane whose x coordinates are from this open interval 0 to 1. 0 is not included and 1 is included, and y coordinates are given by this trig function sine 1 over x. It's connected but not path connected. Okay, let's see the picture of this topology sine curve. Let's say this is our y-axis or is our real line, and this one is our x-axis or is another real line here. So this topology sine curve, that's the union of those two sets. So you can see the first set is nothing. That is just the part of y-axis from -1 to +1. So this is our this is our first set in that union. It's basically set of all order pairs such that x coordinate is 0 and y is -1 and between -1 and +1. That's why it's this curve. And for the second one, x, they are between 0 and 1. Let's say this is 0 and that one is 1. 0 is not included. So this set, it doesn't have the point. It's basically order pair. So since x coordinate is not 0, so is not the second set doesn't have the points on y-axis. Okay, so all the points on the second set, they are to the right side of y-axis, and x is between 0 and 1, and y coordinates are given by this trig function. So basically the graph is gonna be the second set is gonna be is going to be the point on this graph. Okay, it's like this one is gonna be oscillate like this one, and when it comes closer to y-axis, then those graph, they come more closer and closer, and they keep oscillating like this one. And if you use the some computer application, you can see the graph in more clear way. So it's going to be oscillate like this between -1 and +1. So here this black curve and this red, and those two curves together, that is called the topology sine curve. And this curve, this topology sine curve, is connected. It's connected, but it is not path connected. Okay,